Sure, here's the entire text rewritten into a single coherent paragraph, without skipping any words. In recent times, humanity has pulled off amazing achievements in space exploration. We've set foot on the moon, sent robots to Mars, and launched probes to the farthest reaches of our solar system. Still, we're nowhere close to truly leaving our own system behind. Have you ever wondered why we've been able to explore a few nearby planets, but that still can't venture beyond them? Today in the space world, we're going to look into the current limits of space travel and understand why interstellar journeys remain in the realm of science fiction. From the speed of spacecraft to the tremendous amount of energy needed, the hurdles are much bigger than most people imagine. I'll go over these challenges and show what would have to be conquered for us to someday reach other stars. Then you'll see why this might be a problem without an easy solution. The history of space exploration is filled with extraordinary milestones. In the late 1950s, we took our first steps into space, driven mainly by the space race between the United States and the Soviet Union. The launch of the Sputnik satellite in 1957 marked the start of this era, and not long after, cosmonaut Yuri Gagarin became the first human to orbit Earth in 1961. These breakthroughs showed that leaving Earth's atmosphere was possible and paved the way for future crewed missions. The most remarkable achievement of that period was humanity's arrival on the Moon in 1969 with the Apollo 11 mission. That accomplishment proved that no matter how unlikely it seemed, we could achieve huge goals, fueling the dream of one day visiting other planets. Over the years, the focus shifted to uncrewed missions. Probes were sent to distant parts of the solar system, and we saw notable advances like expeditions to Mars and ongoing studies of Jupiter and Saturn. Voyager 1, launched in 1977, is currently at the border of interstellar space, over 20 billion km from Earth. Even so, it's still incredibly far from any other star system, highlighting just how vast space is and how limited our abilities remain. Despite all we've done, we're still confined to our cosmic backyard. Leaving the solar system to travel to other stars would require technology far beyond what we have now. This brings us to a crucial point. Why are space distances such a huge hurdle? One of the biggest barriers to interstellar travel is simply the distance. Even our solar system is enormous. Earth is about 150 million km from the Sun, a measure known as 1 astronomical unit. To grasp that scale, note that Voyager 1, the farthest spacecraft from us, took over for decades to reach the outer limits of our system, and it still hasn't fully left. When we consider moving beyond those limits to reach another star, the challenge grows dramatically. The closest star, Proxima Centauri, is about 4.24 light-years away. 1 light-year is roughly 9.46 trillion kilometers. If we hypothetically sent a spacecraft moving at Voyager 1 speed, it would take around 70,000 years to get there. That doesn't even include the technical difficulties along the way. Even with more advanced concepts like laser-powered solar sails, we'd still only achieve fractions of light speed, meaning the trip could last decades or even centuries to relatively close destinations. This is one reason why interstellar travel remains theoretical. Another big issue is that as distances grow, it's not enough to just make spacecraft go faster. The laws of physics dictate that for each small increase in speed, the energy required grows tremendously. That leads us straight to the next problem. We don't have propulsion technology anywhere near what's needed to cross such vast distances in a reasonable time frame. As if dealing with huge distances weren't tough enough, limited propulsion makes it even harder. The speeds reached by spacecraft today may seem high by earthly standards, but they're nowhere near enough for interstellar travel within the span of a few human generations. Voyager 1, for instance, travels at about 17 kilometers per second, impressive when seen from our planet, but insignificant for journeys measured in light-years. That's because our current propulsion methods are based on basic physics principles that limit a spacecraft's acceleration. The most commonly used approach up to now, chemical propulsion relies on fuels like hydrogen and oxygen, which spark a controlled reaction to propel the craft. This system works to leave Earth and handle relatively short trips in the solar system, but it becomes unfeasible for very long voyages because the amount of fuel needed would be impossible to carry. Research on other types of propulsion is already underway, such as ion drives that use electrically charged ions to create thrust. NASA has used this method on some probes like Dawn, which explored asteroids in the main belt. Ion propulsion is more efficient in terms of fuel, but it provides very low thrust, resulting in very slow acceleration. In other words, even if it's more economical, it would take years to reach velocities that could help on very distant trips. There are also theories about fusion-powered propulsion using the same reactions that take place inside the Sun. In theory, this could provide enough energy to accelerate a craft to a meaningful fraction of the speed of light. However, we still haven't mastered fusion in a practical way, nor do we have the means to build compact reactors for use in spacecraft. Creating a system like that, which is both safe and functional, still seems out of reach. Then there are even more futuristic, or nearly fanciful ideas like solar sails and laser propulsion. One example, the Breakthrough Starshot project, plans to send tiny probes to Proxima Centauri and powerful Earth-based lasers aimed at reflective sails. If it succeeds, they might reach 20% of the speed of light and get there in around 20 years. But it faces huge challenges: laser precision, durability of the tiny probes, and above all, slowing down at the destination. Without a way to brake, these craft would just zip by the star system without enough time to study anything. So the problem of propulsion isn't just about going faster, it's about balancing energy, efficiency, and what technology can actually provide. So far, nothing we have or even envision matches the scale of that adventure. Meanwhile, there's also the energy problem. To leave the solar system and reach another star, the amount of energy required is almost unthinkable. Present-day spacecraft generally rely on two sources, solar and nuclear. Both have major drawbacks for interstellar missions. Solar power works well near our Sun, but it quickly becomes almost useless as distance increases because sunlight weakens drastically. Nuclear power, which comes from radioisotope thermoelectric generators (RTGs), is more promising for long missions. Probes like Voyager and New Horizons use this approach, converting heat from radioactive decay into electricity. It lasts for decades, but still doesn't deliver enough power for advanced propulsion systems. Even if by some miracle we solve propulsion and energy challenges, there's still a fundamental concern: human survival on an interstellar journey. Spending a long time in space brings serious biological and psychological risks we don't fully understand yet. Outside Earth's magnetic shield, cosmic and solar radiation increases the risk of cancer and can harm the nervous system and the heart. Solutions include more robust shielding and materials that absorb radiation, but there's still no reliable way to protect a crew during a flight that might take decades or centuries. On the psychological side, space missions have shown that isolation and confinement take a heavy toll on astronauts' mental health even on relatively short trips. Imagine a crew spending decades in a spacecraft with no in-person contact beyond their fellow travelers. Boredom, loneliness, and lack of external stimulation can lead to depression, anxiety, and more serious psychological issues. Tests like the Mars 500 project showed that these effects can be significant even over shorter periods. Communication is another hurdle. Even within the solar system, sending and receiving messages can take minutes or almost half an hour, depending on planetary positions. For something as distant as Proxima Centauri, a message would take over 4 years to arrive and another for it to come back. Keeping the human body in good shape is also critical. Microgravity weakens muscles and bones, causing loss of muscle and bone mass. On longer flights, The crew would need strict exercise routines to minimize this damage, and even then, it would be hard to fully counter it. But there's an obstacle many consider insurmountable: time itself. It's not just about how long a journey might take, but also about time dilation described by Einstein's theory of relativity. Let's break it down. Crossing interstellar distances can take centuries, complicating any plan to complete it in a single generation and prompting scientists to consider solutions that challenge what we know about time and longevity. One idea is so-called generation. Ship self-sufficient craft where multiple generations would be born, live, and die until finally arriving at the target. The original crew would know they'd never see the final outcome, only their descendants would. This sparks logistical and ethical questions. How do we ensure the technology lasts for centuries? How do we guarantee that future generations will keep wanting to continue the mission? Plus, the first generation would leave by choice, but future generations would be born aboard the ship without ever being asked if they wanted to inherit that goal. It's a deep debate for another time. Another theoretical idea is hibernation or cryogenics. In recent times, humanity has accomplished remarkable achievements in space exploration. We've set foot on the moon, sent robots to Mars, and launched probes to the farthest reaches of our solar system. Yet, despite these successes, we remain confined within our cosmic neighborhood. Have you ever wondered why we've been able to explore nearby planets but can't venture beyond them? In today's exploration of space science, we'll examine the current limits of space travel and understand why interstellar journeys remain in the realm of science fiction. From spacecraft speed to the immense energy required, the obstacles are far more daunting than most people realize. We'll explore these challenges and what must be overcome for us to someday reach other stars, revealing why this dream remains so distant. The history of space exploration is filled with extraordinary milestones. In the late 1950s, driven by the Cold War space race between the US and the Soviet Union, we took our first steps into space. The launch of Sputnik in 1957 marked the beginning, and in 1961, Yuri Gagarin became the first human to orbit Earth. These milestones showed that escaping Earth's atmosphere was possible and paved the way for crewed missions. The crowning achievement of that era came in 1969 with the Apollo 11 mission, humanity's first steps on the moon. That accomplishment sparked dreams of reaching other planets. Over time, however, the focus shifted toward uncrewed missions. We sent probes to distant planets, with notable successes like missions to Mars and the continued study of Jupiter and Saturn. Voyager 1, launched in 1977, is now over 20 billion kilometers from Earth and at the edge of interstellar space, yet still far from the nearest star. This highlights how vast space truly is and how limited our technology remains. Despite all we've achieved, we are still confined to our solar system. The most significant challenge of interstellar travel is distance. Even within our solar system, the scale is enormous. Earth is about 150 million kilometers from the Sun, one astronomical unit. Voyager 1 took over for decades to reach the edge of our solar system and still hasn't fully left it. To reach another star like Proxima Centauri, which lies about 4.24 light-years away, a spacecraft moving at Voyager's speed would take approximately 70,000 years. Even using advanced ideas like laser-powered solar sails, we'd only achieve a small fraction of light speed, and the journey would still take decades or centuries. These long timelines are one reason interstellar travel remains theoretical. Another major obstacle is propulsion. As distances grow, it's not just about going faster. The energy needed increases dramatically. Our current propulsion methods, such as chemical rockets using hydrogen and oxygen, work well for short trips, but are inadequate for interstellar voyages. Carrying the required fuel becomes unfeasible. Research into ion propulsion, which uses charged particles to generate thrust, shows promise in efficiency but results in very slow acceleration, useful only for long-duration, low-thrust missions. like asteroid exploration, fusion propulsion, which could theoretically produce enough energy to travel faster, remains beyond our technical reach. Compact, space-worthy fusion reactors have yet to be developed. Other futuristic ideas, such as solar sails and laser propulsion, are being explored. The Breakthrough Starshot project envisions sending tiny probes to Proxima Centauri using lasers to push reflective sails. If successful, they could reach 20% the speed of light and arrive in 20 years. However, it faces enormous hurdles, from laser precision to probe durability and especially deceleration at the destination. In short, propulsion remains an unsolved challenge. Energy is another fundamental barrier. Solar power, while effective near the sun, becomes virtually useless farther out. Nuclear energy, used in spacecraft like Voyager and New Horizons through radioisotope thermoelectric generators, RTGs, offers more consistency over long missions, doesn't generate enough power for advanced propulsion. Even if we solved both propulsion and energy, we would still face the biological and psychological challenges of human survival on multi-decade or even century-long missions. Long-duration space travel carries serious health risks. Outside Earth's magnetic shield, cosmic and solar radiation increase the chance of cancer and can damage the nervous system and internal organs. While researchers are exploring radiation-absorbing materials and shielding, no current method offers reliable protection for such long missions. Microgravity is another threat, causing muscle and bone deterioration. Even with regular exercise, it's difficult to fully counteract these effects. Mental health is also a concern. Astronauts on short missions already face psychological strain due to isolation and confinement. Imagine a crew confined to a small ship for decades, with no external contact aside from their crewmates. Depression, anxiety, and other issues would be almost inevitable. Communication adds yet another complication. Even within the solar system, messages can take minutes or nearly an hour depending on planetary alignment. With Proxima Centauri, a single message would take over 4 years to reach its destination, and for more to receive a reply. This delay makes real-time interaction impossible. Then there's the issue of time itself. Interstellar journeys could take hundreds or thousands of years, depending on the technology. One proposed solution is the generation ship, a massive spacecraft where several generations live and die before reaching their destination. But this idea is fraught with logistical and ethical questions. How do you ensure the ship remains functional over centuries? How do you motivate future generations born aboard, who never chose to take part in the mission? Another theoretical idea is hibernation or cryogenic sleep, slowing biological functions to allow the crew to sleep through the trip. But this remains purely science fiction. We have no way to safely suspend and later revive humans for such extended periods. Even more exotic ideas like warp drives, wormholes, or space-time manipulation exist only in theory, with no practical foundation. Einstein's theory of relativity adds a further twist: time dilation. As spacecraft approach light speed, time slows for the travelers relative to those on Earth. So, while only a few years might pass for the crew, decades or centuries would pass back home. This creates a disconnect that makes round-trip travel or interstellar colonization even more complicated. A ship traveling at near light speed would essentially become its own isolated civilization. All of this leads to a sobering reality. Interstellar travel, while inspiring, remains far beyond our current capabilities. Space exploration is still in its infancy, and exploring even our solar system in detail may take millennia. As for the Fermi paradox, if the universe is vast and full of life, where are all the aliens? The simplest answer may be that, like us, other civilizations are also stuck in their own stellar neighborhoods. The universe's vast distances make travel between stars nearly impossible, regardless of intelligence or technology. This doesn't mean aliens don't exist. It just means they, too, might face the same cosmic limitations. No warp drives, no shortcuts, only the slow, steady march of science. What do you think? Does the universe truly prevent us from exploring it the way science fiction imagines? Or might an unknown discovery someday unlock the stars for us? Let us know your thoughts, and if you enjoyed this deep dive, don't forget to like the video and subscribe for more. Thanks for watching, and see you next time.